All right, here we go. I don't have my computer, so you have to get this as I write it in the screen capture, but it is what it is. All right, so properties of solids. This is all review from last year, so or 2 years ago, this should be good. And so very quickly, we'll do a comparison of the states of matter, just so we know what we're doing. So you have your 3 states of matter. So we have solids, we have a liquid, and we have the gas phase. So remember that with solids, your atoms would be really close to each other. All right, so things you should already know. They have a strong attraction. So that would be like strong IMFs, or they have strong chemical bonds holding them. They are in a fixed position. That's why solids have a definite shape and a definite volume. But they do move. So please remember that your atoms do vibrate in place. When we come to a liquid, all right, so your particles are a little bit more spread out. They take the shape of the container, but they still stay near one another. So liquids have, we'll call it less attraction than solids. So remember that your liquid particles can move past one another. Okay. And then for gases, remember they fill up their container. Okay. They're really far apart from one another. The third section of this unit is all about gases, so we'll get to revisit all of them. So they have low to no attraction, and we'll talk about that. Last year we assumed no attraction, but we will talk about kind of how that works. They move very quickly, and like I said, we will, the third part of this unit, so you get 2.5 or 3 days in class of all about gases. All right, so we get to revisit that. Sometimes AP will make you draw like a certain molecule as a solid, a liquid, or a gas, like to show how the particles are. So like if we looked at something like I2, all right, I2 as a solid, it is a diatomic. So like as a solid, it would be in pairs. And then those pairs would all be really close to each other. Kind of neat and organized. It's the best I can do. So that's solid. As a liquid, those 6 would be a little further apart. And then as a gas, we would show that it's entirely much further apart. If it was something that wasn't a diatomic, like what if it's just, I don't know, helium. If it was something like helium, well, we would show helium as just a single atom. So again, as a solid, it would be more like the pictures that we have. They would all be really close to each other. As a liquid, and then as a gas. All right, so be able to show like the 3 states of matter, or at least show a change between them. And remember that when you are changing between them, it is a physical change. All right, so now these are the types of solids from your reading yesterday. So things to know about metallic, or what you should have gotten out of essentially what we did yesterday. Well, you should already know metallic solids are metals. That's kind of in the name. They are held together. Your atoms there are held together by metallic bonds. And remember that since it is metallic and not covalent, there are no IMFs. The only attraction that exists in a metallic substance are metallic bonds. Okay? Properties about them that you need to know. And the properties are honestly the key to identifying what kind of bond are there. So you need to know these properties because it's very common that AP will give you like data table of various properties and ask you to decide who's metallic or who is a covalent network. All right, so you need to know these things. So the first, they are conductive of heat and electricity. And that's probably the easiest way to tell something as a solid is metallic. The other ones don't conduct as a solid, so that's just your best option to know something is metallic. Why is it metallic? Remember that with the sea of electrons, your electrons can move. So that movement, you have to have free moving particles to be able to conduct. So that movement of the electrons allows you to conduct heat and electricity. Number 2, all right, they are malleable, ductile, easy words, they're bendable. All right. So they don't break, they're not brittle, they don't crumble when you apply force to them. So this little picture is your Y. So there's your kind of metallic bond. There's your little metal atoms. The little blue dots are your electrons. Here is what you apply a force. Okay, so you bend it, you push it, whatever. When you do that, it shifts your atoms, but notice that like they're all still able to attract to one another. Okay, so you're still able to attract to those delocalized electrons, that sea of electrons. So remember that that is why they are malleable and they don't crumble and break. 3, they have incredibly high melting and boiling points. And from yesterday, you should have gotten that ionic, metallic, and covalent networks have the really high ones. And again, your Y has to do with the fact that they're held together by actual bonds. You have that strong attraction between the nuclei and those delocalized electrons. And your last thing about them, almost all of them are solids at room temperature. And in case you're wondering, room temperature is 25 degrees Celsius. The notable exception is mercury. It is a liquid metal. And again, your Y, you're held together by actual bonds. So the strong attraction of metallic bonds. All right, second type of solid, which you should already kind of know. We have ionic, so things you should review. Typically, it's a metal with a nonmetal. We transfer electrons. All right. We make our cation and our anion. Again, we are held together by ionic bonds. And I can't say this enough, there are no IMFs in ionic. All right. You will only have ionic bonds in ionic substances. And remember that they make our lattice structure. So that's kind of key things. Where you have the positive, the negative, the positive, the negative, the positive, the negative. And you need to be able to recognize which picture goes with which type of bond. Okay? So if we do our properties that you should have gotten out of yesterday's readings. 1, they have high melting and boiling points. All right, we can talk about the Y. You should know this. So Y, you have a high attraction between the ions. we already talked about how to decide within ionic compounds who's higher. Please remember, we do charge first, then distance when you're looking to make that decision. That's all from last unit. Second, they are all solids at room temperature. Always, right? Why? Again, high attraction. When you have a true cation and an anion attracted and they make that lattice structure, you just get a lot of attraction that's holding your ions together. All right, in terms of your pictures, your third property about them is to deal with their conductivity. So conductivity is probably the easiest way to classify them if they give you conductivity data. Metallic conduct as a solid. Ionic will not conduct as a solid. So not conductive as a solid. And your why. So why are they not? Your ions can't move. All right. So ions are held in too tight of a place and they can't move. And if your particles aren't moving, you can't conduct electricity or heat. But if we take an ionic substance and we melt it, so that's what molten means, or we dissolve it in water, so that means dissolve in water, then it will conduct. All right, so will conduct as a liquid or dissolved in water. So to conduct, you need a charged particle that's moving. I guess I should have said that earlier. So with metallic, you have negatively charged electrons that are free moving. That's why metals can conduct. In ionic, once we melt it and we turn it into the liquid phase and your particles separate some, or we dissolve it in water where the pluses and the minus separate, now you've got charged particles that are able to move, and now it will conduct electricity. Okay. And the last characteristics of ionic is that they are brittle solids, okay, which means if you smash them with some pressure, they'll crumble. So reason is, if you take a little, again, atom-sized hammer and you apply a force, when you cause your ions to shift, you get positives next to positives and negatives next to negatives, and then they repel. And that is why it is brittle and it will crumble. Okay. Your last two types of solids are both covalent bonds, but they're a little bit different. All right, so this third one is kind of a special group of covalent network solids. They're called covalent network solids. They are held together by covalent bonds. And essentially, we say no IMFs for them either. It is all bonds, so all lines between the atoms. All right. Examples that you need to know, all right, that would make a covalent network, because there's a limit to these. So examples to know would be carbon, which is either graphite or diamond. Okay. And that's a little picture over here. You can see the diamond. So every carbon, this is a carbon, is attached to 4 other carbons in a tetrahedral shape. And again, there are actual bonds between them. And we drew this out last year, so if you wanted to draw it, it would be like this, where everybody just keeps connecting. That's why they call it a network. Okay. Your other example you need to know would be silicon, so Si, and Si compounds. With the exception, SiH4 would not be, because H's can't make more than one bond. So SiH4 cannot make extra bonds around. But silicon dioxide, which is what glass is what this structure is. Okay. So each silicon actually has 4 O's around it, and then Those O's bridge to another silicon who has O's, and again, they make this giant structure. Okay. Another one is silicon carbide, SiC. So silicon compounds, except for SiH4, because SiH4, as soon as you bond your H's, you can't make a network because your H's aren't allowed to have extra lines. Okay. And probably the thing you do need to know about them, they have extremely high melting and boiling points. All right. And then your last group are the other type of covalent, which we call molecular solids. All right. They're also covalent. All right. But they exist as molecules, like individual molecules in nature. Essentially, these are the ones we draw Lewis structures for. Right, we just did a whole bunch of those last unit. This is where all of your IMFs come in. So they have IMFs between those molecules. Or just individual atoms if it's a noble gas. Okay. So remember, you would have X bonded to X, and then we'd have our dashes that we talked about the other day. Bam. Those are the attractions that exist between them. In comparison to the other three types of solids, these ones typically have very low melting and boiling points. And you would be able to compare them based on your IMFs. Right? And then again, these are not conductive. That you should know from Honors Chem. That covalent things do not conduct as a solid. Covalent things do not conduct when they are dissolved in water. Okay. All right, so your old AP question. So it says account for the following observations about pairs of substances. In your answers, use appropriate principles of bonding and IMFs. You must include both substances. So when I do something like this, I typically look at my two things that are in my question. So in this case, we have silicon and we have Cl2, and I think about what kind of solids they are. Okay, like that should be the first thing. Which of the four categories do they fall into? When I see Si, you need to think covalent network. Pure carbon, and then Si. Cl2, you need to realize it is covalent because it's non-metals, but it's not one of the special covalent networks, so it would be a molecular solid. And you would have to think about its IMFs, and the only IMF that it has would be LDF. Okay, so think about the kind of solid it would be and what attraction it would have. Your Si is a covalent network, so it has only covalent bonds holding it together. So you're going to make your claim. What I already told you the claim. Si melts higher. Your evidence is going to be the bonds, and then we're going to talk about why does that matter. All right, so in our answer, we would say, it's like all the info we need to be able to answer it. So in our answer, we would say Si is a covalent network versus Cl2 is molecular. Okay, so there's the difference. Why does that matter? Si is held together by covalent bonds versus Cl2 is held together by LDF, London dispersion forces. Covalent bonds mean a higher attraction, again, because they're actual bonds, not just an attractive force, giving Si a higher melting point. And our second one, again, whenever I'm comparing two things, All right, we have MgO, we have NaF. All right, well, MgO, which of the four does it fall into? It's ionic. It's a metal with a nonmetal. NaF, also ionic, metal with a nonmetal. So we can't argue this one based on the types of bonds because they're both the same. Okay, so it's different than that first one because we can't argue in the way we did. So when you do ionic, then you got to think Coulomb's law, and we do charge first, then distance. So our argument here would be that both are ionic. All right, so we can't go from there. So we would say both ionic. All right, now we have to figure out the difference. Well, MgO is 2 plus with 2 minus, while NaF is 1 plus with 1 minus. Okay, why does that matter? What does Coulomb's law tell us? As we increase our charge, we will increase the attraction between them, and we will increase the melting point. Thus, MgO's is higher.